Okay. So maybe let us start with the first talk of the morning. So it's my pleasure to introduce Anne Peters from the University of Amsterdam. And this talk is titled Using Complex Dynamical Methods to Describe the Computational Complexity of Approximating the Independence Polynomial.
Thank you, Mathieu. And thanks to the organizers. Of course, I would have preferred to come to Barcelona again, but it's very nice to see everybody. So thank you, organizers, for getting this together despite the Corona crisis. I should also apologize that I haven't been here much this week, and probably I won't be here often in the next 2 days because of family reasons, but I'll try to attend at least a few more lectures. I'm going to talk about a topic which is on the edge between complex dynamics, graph theory, a little bit of theoretical computer science, and statistical physics. So it's a lot, but let us start in our comfort zone and look at some complex dynamical systems. So here I added 2 pictures, very simple pictures. They are, maybe you think, okay, that looks like the Mandelbrot set. In that case, you'd be right. They do look like the Mandelbrot set. They are the activity loci of a different rational function, namely lambda. So if you prefer, I think C, lambda is the parameter, lambda divided by 1 plus z to the power d. For there are 2 pictures. On the top right, there is the degree 3 picture, and on the left there is the degree 4 picture. And you see they look quite similar, and they look quite similar to the Mandelbrot set. Here is what you might call the main cardioid, though it's not formally a cardioid. But there you converge to an attracting fixed point. Here on the exterior component, here and here you converge to an attracting cycle of periodic 2. So that's a little different from the Mandelbrot set. But you see, you have all these hyperbolic components that you see each associated with some period. I drew these pictures by computing the spherical derivative of, I believe, the 120th iterate of the function. I didn't actually compute the spherical derivative. I just computed a grid of values and approximated the spherical derivative, and used the white means very large derivative, and blue means bounded derivative, and yellow is slightly larger derivative. So white is should show where your functions do not form locally a normal family. Well, what can we say about these sets? A lot, but you can make by the universality property of the Mandelbrot set, you can make the relation with the Mandelbrot set more precise. But there's something else I want to stress here, namely that the activity locus, so the parameters where this family is not normal for fixed D, this equals the 0 set, the closure of the 0 set minus the zeros. So notice that there's only one critical orbit here. Minus 1 is mapped d to 1 to infinity. Infinity is mapped d to 1 to 0, and well, etc. This is, we have counted all the critical points, so the only critical points are -1 and infinity. And if 0 is mapped after a while to 0, then we have a super attracting fixed point. So we are in, this is stable, we are a normal family. On the other hand, if you avoid 0, then you also avoid -1 and infinity. So you are a normal family by Montel. So you see that zeros must accumulate on the activity locus, while they all do not lie. They must accumulate on the whole activity locus. So you have this relationship between normality and the zeros. All right, and you can prove more in each hyperbolic component, just as for the Mandelbrot set. There is a unique center. There's exactly one parameter for which you have a super attracting fixed point. And well, you have to interpret infinity as the center of the unbounded component. Okay, so I imagine that you're all comfortable with what I told you thus far. Let me show you a different picture, which is, now I put activity locus in quotes. This is again a picture where I approximated the spherical derivative of some rational function. And in fact, again, it's a family of rational functions whose degrees grow to infinity. And as the degrees grow, these pictures converge. And this one is of degree 506. And recall, here I had degree 3 or 4 to the power 120. So it is incomparable. And you see also that it seems like the resolution is less. It's not true. The resolution is the same. But, well, the polynomial, I cannot do it for a large degree polynomial. In fact, I cannot do this at all. This polynomial was, or this rational function was computed by a PhD student in my department who's doing a PhD in numerical analysis, and he has access to a supercomputer. And on the supercomputer, we could generate this rational function. So this rational function is not dynamical. It's not the iterate of some polynomial or rational function. However, the picture that you're seeing resembles very much the pictures that we saw above. And that's why I'm calling it also an activity locus, even though it's really, the yellow represents, or the white represents where the points where a family of rational functions is not locally normal. But a lot of properties seem to be preserved. Here you seem to have something which you would call a main cardioid. And in fact, we do know that as your degree gets larger and larger, you converge exponentially fast to a unique limit here. And on the unbounded component, you converge to something of period 2. And there seem to be infinitely many components. So we could call them hyperbolic components. But really, we don't understand this picture at all yet. So these polynomials, of course, they're not random. They come from physics, and they are, in fact, physically much more relevant than the iterates of these rational functions that I showed you, even though they also come from physics. So these are much harder to understand, much harder to draw the picture, but they are exactly what the rational functions that a physicist might be interested in. So let me explain where this comes from in physics very briefly, and then I'll also say something about the theoretical computer science questions that I'm interested in. So in physics, this comes from the hardcore model. And imagine that you have here a layer of graphene, which is a two-dimensional grid made of carbon, like this, hexagonal. And suppose that next to this graphene slab, we have a helium gas. So here we have atoms, and then some of these atoms can be absorbed in the holes of the graphene. Okay, so let me draw here. There could be a helium atom, and then here could be another one. However, even though these atoms are very light, they take up a fair amount of space, too much to lie next to each other. So here there cannot be a helium atom. Now this graphene lattice, it is of course incredibly large. So we imagine that it's really an infinite lattice, or a rescaled limit of larger and larger finite lattices. So we could be interested in questions such as, what is the probability that this hole is filled with an helium atom? Or, since all the holes are similar, what percentage of the holes could we expect to be filled by helium atoms? And another question is, how does this percentage vary as your parameters vary? For example, as your temperature vary. As your temperature gets larger, maybe atoms want to be less absorbed. And it turns out that typically things vary analytically, but not at all parameters. You could have parameters where these physical properties do not vary analytically, and then we speak about phase transitions. Another question that you could ask is, can you actually compute this probability that a given hole is filled with a helium atom? And it turns out the answer is no. No, you cannot. For a large lattice, you cannot actually compute it. It's too difficult. Then you could ask, well, can we approximate it well? And that also depends on the parameter. So is there an efficient algorithm that approximates this probability well as your graph gets larger and larger, as your finite lattice becomes slowly infinite? So efficient means that it runs in time that's polynomial in the number of vertices. And so the answer to that question is sometimes. Sometimes you can do it. It depends on your parameters. And in fact, it turns out that the two questions are almost the same. Whether you can actually approximate the value is related to whether this value depends analytically on your parameters, and both are related to the zeros of some polynomials. So what are those polynomials? They're called a specific graph polynomial, the independence polynomial. Which is a polynomial z that depends on a graph G. So a graph G, which is some points and some edges between the points. And it depends on a number, lambda, the parameter, which could be real if you're a physicist. But if you really want to understand what's going on, of course, you should consider complex lambda. And what's the formula for this polynomial? It's you consider all i's subsets of the points, where you only consider independent subsets, and you take lambda to the power the size of v. So a subset I of v is independent if no two vertices in I are adjacent. So you can see already the link with this graphene. Here we always take so you have a dual graph, the holes, and the holes filled by atoms. It must be an independent subset of that graph. Could be any independent subset, but no two atoms may be adjacent. Okay, and then the energy is related to the lambda, some parameter, to the power, the number of vertices that are filled. So let's do an example. This quickly goes out, becomes way too large to actually compute, but let's take a very, very small graphene piece. So here is the dual graph. I have 7 points here. Then the independence polynomial is 1 for the empty set. The empty set is independent. Plus, and there are 7 independent sets with 1 vertex. There are, how many are there with 2? There are 1, 2, 3. If we take the top point, and there are 3 other choices for the second point, you cannot choose the middle one. The 4, 5, 6. I think there are 7 lambda squared. And there are also 2 possibilities to get 3 points, right? You could have this one, and this one, or you could have the other 3 outside nodes. You can never have the middle one if you need 3 vertices. So if I counted correctly, this is the independence polynomial. And notice that if you enter 1, this gives you the number of independent sets, independent subsets, which it seems like this is here 17. Now, as your graph gets larger and larger, it is very hard to compute the number of independent subsets. So this is what's technically called sharp p-hard. Maybe you heard of NP-hard. The question, is there an independent subset of a certain size? That would be an NP-hard problem. And counting the number, so sharp p is the counting version of an NP-hard problem. So it is more difficult than an NP-hard problem. Of course, we don't actually know whether NP is P. Probably it's not, but this is one of the millennium problems, I think. So we cannot say that if a problem is sharp p-hard, then there does not exist a polynomial time algorithm, but probably there is not. So the question is, the question that we're after is not, can we compute this polynomial, but can we approximate this number in polynomial time? Where time in terms of the number of vertices of G. And we should also perhaps restrict the class of graphs. So I'm going to say for graphs in G delta, which I will say this is the family of graphs of maximal maximal degree at most delta. Maximal degree, the degree of a graph is the maximal number of edges that comes together in a single point. So here's a fairly recent theorem of Patel and Rechts, two combinatorists. I think it's from 2017, two combinatorists in Amsterdam. They proved that the answer is yes on the maximal open set containing open component, I should say, open connected set containing zero, which is zero free. In other words, if you have some open connected set containing zero, and you know that for any graph in your collection G delta, you don't have zeros there, then on that open set you can approximate the values of your independence polynomial efficiently, and well, up to some small multiplicative error. And the method, well, first you use the Riemann mapping theorem to get the unit disk, and then you look at the Taylor expansion of the logarithm of z, and you look at, well, how many of these coefficients do I need to approximate to get a good enough approximation up to an additive constant of the logarithm of z. So that's in two sentences the proof of the theorem. So this already relates the approximation to the zero sets of a family of polynomials. Well, I'm going to now translate it to a family of rational functions, and these are called the occupation ratios. So now I'm going to take on my graph, I'm going to take a marked vertex. Then the ratio of my graph and my marked vertex at lambda is z in divided by z out. It's sort of the probability that my point is absorbs an atom. It's here I only consider only independent subsets I with the marked point lies in I, and here only subsets that do not contain the point, right? So that the terminology in and out comes from that definition. So this is a rational function. And note that z is of course z in plus z out. I dropped all the subscripts, but if you want to sum over all independent subsets, you should take this independent subset that contain v and the independent subsets that don't contain v. So hence z is 0 if and only if r, which is z in divided by z out, is -1. Well, it's not exactly true, but because they could both be 0 and you could have some cancellation. So the rational function might not actually be -1 if you have 0 divided by 0. So let me put this in quotes and ignore that problem. It is not a problem, but it's something you have to be careful with. So the zeros of z are corresponds to the -1s of the ratio. Now, here is a theorem of an Hungarian combinatorist, Benz. Let me say from 2019, something like that, which says that for any graph G, there exists a tree T. So this graph is, let's say, in G delta, then the tree is also in G delta, same maximal degree, with the ratio of the graph with the marked vertex equals the ratio of the tree with the marked vertex. So in other words, if we want to study the -1s of ratios, which we now want to do, then it's sufficient to only look at trees. So that's nice because trees, they're built recursively. And in fact, also we can compute the ratios recursively. So if you have a tree, let's say here, T1, T2, T3, and here's your whole tree T, then it's easy to check that the ratio of the tree, and here its neighbors V1, V2, and V3. The ratio of the tree is given by lambda divided by the product of 1 plus the ratio of Ti and Vi. So we can express the ratio of the bigger tree in terms of the ratios of the 3 subtrees. Now this is not, you may think that I'm still working towards efficient approximation. This is not in no way an efficient way to approximate the actual values of R or of Z, because in this theorem of bench here, so there exists a tree for which the ratio is the same as the ratio of the graph. But as your graph gets large, this associated tree, it gets exponentially larger. It is very, very inefficient. And also already a lot of work to write down this tree. Your computer may not even be, even for a not too large graph, your computer may not be able to contain the information for this tree. So this is not the way to go, but it's useful for proving things. So having this dynamical interpretation of ratios allows you to use methods from complex dynamics. So note that if T1 is T2 is T3, let's do it in general up to Tk, then RTV is lambda divided by 1 plus RT1 to the power k. And this already looks a lot like the rational function I started with today. So when does that rational function comes up? It comes up when this property holds at every level of the tree. So imagine that you have a tree where at every level, except at the leaves, you have the same down degree. And all the leaves have the same distance to the top vertex. So now RTV is FD to the n times iterated of actually of 0. Because if you just have one point, then the rational function will be lambda, which is just the image of 0. So maybe I should write here n plus 1. Okay, this circle I will not use again for iteration, but here you see that for a very pleasant recursively defined family of trees, you get exactly the dynamics of the rational function I started with today. And these are called Cayley trees. And well, so you had some cardioid here, and then you know this region is 0 free, but zeros accumulate on the boundary. This is 0 free for the cardioid. So if you consider all graphs of that same maximal degree, then there could still be zeros. So the maximal 0 free domain for given delta is a subset of the main cardioid. And some combinatorists conjectured that maybe it's equal, but that is way too much to ask for. For example, instead of using the same down degree at every step, you could at each level take a different degree. Then you don't have iteration of a given function, but you have a finitely generated semigroup of the functions f1 through fd. And my PhD student, Piotr Buys, showed really in the first month of his PhD project that it's not an equality. You have some in the semigroup you have some curves where you have neutral fixed points for elements of the semigroup. So really you can use many ideas from complex dynamics here to describe this set. But that is not what I want to do today. I don't want to say more about what this set is. I want to show that that there are many equivalent ways to define this set, this maximal 0 free set. Okay, so we have the 0 locus, which is the closure of the lambdas for which there exists a rooted graph with for which lambda is a 0. And I take the closure of that. I'm going to write down several closed sets. So this is the 0 locus. I also have the activity locus, which is all the lambdas for which the family, let's say lambda naught, for which the family lambda goes to R GV of lambda is not locally normal. So my family here is a family as I vary the graphs, right? So my graphs G are in G delta. I consider all possible graphs of some maximal degree. So that's my definition of the activity locus. It's already closed, so I don't have to take the closure. Then a third notion is the density locus, which is all the lambdas for which, if you consider just the values at that point lambda, where again you vary your graph G. This is dense in C or in the Riemann sphere, of course equivalent. And this is an open set. It's not immediately obvious, but it is. This is an open set. So we take the closure of that. And then the last set is the Sharpie locus. Well, let me say that this is lambda. Now I really want to consider, it doesn't make sense to consider hardness for real parameters. You should really look at rational parameters. So we should look at Qi. I won't go into details here, but you want to look at rational parameters for which approximating Z G lambda is Sharpie hard. In other words, well, I want to say there's not a polynomial algorithm, polynomial time algorithm, but I can't say that. But what you can say is that if there is a polynomial time algorithm for that lambda, then there also exists a polynomial time algorithm for computing the number of independent subsets. So well-known Sharpie hard problem. That's usually how you deal with these notions. Okay, so I have 4 different loci, and we have a theorem with 2 PhD students in Amsterdam, De Boer and Buys, and Rechts, my colleague, and myself. And the first 3 loci are equal, and they are contained in the 4th. We would like to say that they're all 4 equal, and we think they are, but we haven't proved this yet. And that may be a very difficult problem. We don't know. If we could prove that the complement is connected, so if the complement is, if there's just 1 0 free component, and it sure looks that way, and we have heuristics to suggest that it really is connected, then you always also have equality with the 4th. Okay, so we have these I would like to say 4 equivalent notions: the closure of the zeros, the set where you're not a normal family for an associated family of rational functions. Then we have density, which is different because there we take a fixed lambda and we look at all the values that you can get. And then the last one is whether approximating the polynomial is a difficult problem. And I would also like to say that these notions, I'm talking only now about the independence polynomial, which comes from the hardcore model in statistical physics, but you can define these notions for many partition functions in statistical physics. For example, also for the Ising model. And then for the Ising model, it's they are well understood and they're also known to be equal. And it would be nice to investigate equality of these different notions, for example, for the Potts model and for more difficult models. So that could be a next step. I see that how much time do I have left, Mathieu? About 5 minutes?
10, I think.
10 is 10, and then after that, questions?
Yes.
Okay, great. So let me say something about the proof. So one important idea I already told you, namely that you can always work with trees. So when you work with trees, you have these this recursive interpretation of ratios. So that's central in the whole proof. The easiest step is this one. If you have no zeros, then you have normality, which is just a consequence of Montel's theorem. If you have no zeros, then you don't have infinities either, and you don't have -1s either. So you miss 3 points, so you're a normal family. So what does that mean? It's 2 negations, but I think it means that the activity locus is contained in the zero locus. But I may have it exactly the wrong way around. But so there are several other inclusions. Let me try to explain one key idea, which is implementation. Then if you have a graph, let's say we have a graph G, and let's also look at some tree T with a marked vertex V. Then what we could do is we could attach to each vertex of G, we could attach a copy of T, and we attach it at the marked point V. So this is we hang T under each vertex of G. Then so here are these different trees. Then what you get is that the ratio of, let's call this one G hat, the big one, the ratio of G hat at lambda equals the ratio of G composed with the ratio of T. So you can compose functions. And the Cayley trees is very particular. Well, it's not quite the same as this. So this is called implementation. And one implementation we use a lot is in the simplest graph you can imagine, namely a path. So here we have a path, and under that we hang some trees. Up to TK, and here is still our marked vertex of the bigger graph G, which also happens to be a tree. Let's write xi I for r ti vi of lambda of 0. No, sorry, of lambda. Probably doesn't matter to you, but let me try to get it correct. Then our G V of lambda is the composition of a number of functions where these xi's, they are the parameters of these functions. So phi, this is just a Möbius transformation. Where the psi is the parameter. So you can, suppose that you can get a number of different values, then you can implement them, and suppose you can get psi1, psi2, and psi3 different values, then you can implement them and you get a whole bunch of different values, because you can compose in any order these three associated Möbius transformations. And it turns out that if you can choose your your three values well, then you can approximate any value in the complex plane, and even you can do that by, if you take the right order, you can do that exponentially fast. So the distance that you get shrinks exponentially faster than the number of trees that you need to hang. And therefore, this is very useful, for example, proving that density implies Sharpe hardness, because really what you do is you mimic the computation of the G1. Right? So you can, if you get three suitable values in the complex plane, then you can approximate the value 1 exponentially fast. And that you can implement again in your favorite graph. But if you do that, it means you can approximate ZG1 very well. But approximation of something that's a whole number gives you actually computation. So so if you have density and you can approximate the values of your rational functions well, of your polynomials well, then you can also compute the number of independent subsets. So that's another step in the proof. But really, this implementation in paths comes back many times. Now, I was hoping to touch another subject, namely actual understanding of what the set is. Let me show you one picture. This one here. So here is again the main cardioid, the big picture. So this is the main cardioid. In different colors, red, orange, green, purple, are sets which are known to be zero-free. So you see that most of it we don't know yet. So these are 4 different papers where zero-free sets are proved. A new result here is that this region cannot be zero-free. It's a whole neighborhood of the boundary of the main cardioid, except for the 2 real points. The 2 real boundary points. It was already known. You can those lie on the boundary of your zero-free region. And here the method is well, ideas that I discussed above, plus transcendental dynamics. What we do is we let the degree go to infinity, and in the limit you obtain some exponential semigroup involving exponential functions. These exponential functions will have neutral fixed points on the boundary, and then you can show, well, in a neighborhood of such a neutral fixed point, if I say it very shortly, because my time is up, but near any neutral fixed points, you can show you cannot be in normal family there. Okay, that's what I was hoping to say. Thank you very much.